Technology has made a lot of advancements, but one critical area has struggled to make huge gains, and that is with batteries. Storing energy is critical for so much of our world, but advancements in battery tech have been hard to come by. Advancing battery technology is also important to national security. So today we're talking with a company that is working to make big changes. I have with me Francis Wang, CEO of Nanograph, a Chicago-based company that is making silicon batteries a reality. So much of battery development is focused on the cathode, the positive end, and not much has been done with the anode, or the negative end. By swapping out the graphite anode for silicon, we can have denser, longer-lasting batteries that don't rely on sourcing materials from adversarial countries. So let's talk with Francis about the state-of-the-art in battery tech. Welcome, Francis.
Yeah, hey, Chris. First of all, thanks for having me. Very excited to be here and talk silicon, nanograph, and batteries.
I love talking about batteries because literally battery technology is probably the most important technology right now. Because while so much of our world has advanced, battery technology is really, really difficult. And, it's a fairly mature technology, I guess, in the sense that a lot of the designs for, these existing batteries were built a long time ago and designed a long time ago. And changes have been largely incremental in the space. And it's been focused largely on the cathode, which is the lithium ion part and all that, right? And where all the problematic minerals are, the lithium, the cobalt, things like that. But you're focusing on the other end of the battery, the anode end. So I'm very excited to hear from you about all this because I think this is such an important area. But let's start off. I've been sort of talking about why I think battery technology is so important. Can you speak to why battery technology is so important?
Yeah, absolutely. I think, with the advent of the cell phone, so in the late 90s, mid to late 90s, we started seeing this sea change of portability and mobility, right? It started with consumer electronics, and that has slowly progressed into things like electric vehicles. And I think beyond that, we're even looking at things like drones, which are already out there. These all require you to cut the cord, if you will. And so batteries become a very important part of that. How long they run, how fast they can charge and discharge, and, these days, how much they cost.
So many devices use batteries. I mean, and lithium ion type of batteries too, where they're, just very, very small ones, like from headphones and all sorts of things like that. But on the other end of that, we need a lot of like if we're going to do solar and things like that, right? We need battery technologies for that end of the spectrum as well, right?
Although the electric vehicle wave's already here, I think the next frontier behind that where you're really going to see an impact of storage will be grid scale energy storage. And so there's maybe 10 different types of ways to store energy, some of them better than others. It really depends on the application, but you can still apply lithium ion to distributed energy storage is what I call it. Things like a power wall, for example, where you have solar on the roof of your house. You don't want a trailer full of batteries in your backyard, and you've got these little units of distributed energy storage. And that distributed energy storage, let's say in your neighborhood, helps to balance the grid. So we're burning less coal or fossil fuels that we would otherwise just completely crank up on a hot summer day.
Like you said, with EVs, now all of us are, putting large battery packs into our houses now.
it's exciting to see this, right? So I've been doing this for 25 years. I started at a company called Duracell. That was the
We're
best place
familiar
at
with
the time.
Duracell. I've heard of that
Familiar
company
with
before.
For sure. We at the time it was the best place to work on batteries,
Yeah.
but now you're just seeing it everywhere, and it's a global thing. I think, especially in Asia, where arguably they dominate the battery industry, but this is a global thing, and the applications that we're beginning to see that are enabled by energy storage or batteries is, yeah, it's mind-boggling. It's really exciting.
There's been a lot of slow progress. It's been slow incremental progress in making batteries better. But I mean, over time they have gotten substantially better. Can you talk a little bit about like what's so difficult about battery tech that it really makes it hard to make big advancements?
Yeah, you're right. So if you look at the history of lithium-ion batteries, I think we've gone through spurts of, certain technologies making a difference. In general, though, I will say the battery industry is conservative. So the technology cycles are long. And when I say long, it could be decades where you have a certain type of cathode or a certain type of anode or separator, et cetera, that they use for a very long time. You very rarely, if ever, see a disruption in the industry or disruptive technology come along. It just doesn't work that way. And I think
Right.
part of the reason is the safety aspect, in my view. I think it's
Mm.
conservative. The industry in the past has made mistakes. They put something in that's new too quickly. And the problem with lithium-ion batteries, when they go wrong, it's quite dramatic and spectacular, right?
Right.
In a bad way. So that's part of the problem. The other part of the problem is on the technology side. So we all, and when I say technology, I focus on the materials just because, again, historically, it's the advances in lithium-ion batteries come from the materials.
Mm-hmm.
New materials are hard to develop. And in batteries, they make up over 70% of the bill of materials is batteries. So they not only control the performance of the battery, but because they make up so much of the battery, they also make up most of the cost of the battery.
Right.
And so people are always, searching for new combinations, new architectures, new chemistries that get a better performance at a cheaper cost. And that's not easy to do, right? Periodic tables, limited, and, scientists, electrochemists have been at this for hundreds of years. So, it really does take quite a leap to get something that's new and that works well with all the other components in the battery.
I mentioned, there's sort of the anode and the cathode, and the cathode is sort of the lithium part that, so much focus has been placed on. First of all, can you talk about kind of how a battery works, the anodes and the cathodes, and why you decided to go and look at the anode side of things here?
Yeah, a battery at a fundamental level, you'll remember this from General Chemistry 101.
I don't remember anything from General Chemistry 101, so.
Okay, well, I won't go too deep into it, but there's a reduction and an oxidation, a redox reaction that happens within a battery.
Right.
And it allows us basically to store energy in a battery. In the case of lithium-ion batteries, the lithium is shuttled between the anode, which is the negative side, and the cathode, which is the positive side. As it shuttles back and we charge it back and forth, it basically stores the energy on one side or the other. And when we discharge it or use it in our cell phone, we're moving lithium ions to the other side.
So the anode is the negative side of the charge, the minus end of the battery. And that's where you've been focusing your efforts. Can you talk about why you chose that and how you're making improvements there?
Yeah, it's kind of twofold. I've been in the battery industry over 25 years. You kind of see a progression of things.
Sure.
Through the 90s, there was so much effort focused on the cathode, right? Because that was the biggest problem at the time in terms of safety and costs. That, had an incredible amount of innovation within that decade. But you began to see the performance of lithium ions batteries plateau, right? And so it's pretty clear very few people were working on the anode. And if we were going to make continuous progress in a lithium-ion battery, we'd have to look towards the anode. And so fortuitously at that time, I'd always dreamed of becoming an entrepreneur. I was sort of late to the game, if you will. I was in my 40s. Had this dream and burning desire to make a difference, if you will, to move the needle.
Sure.
So coupled with the fact that I knew or I had a pretty good sense that there'd be a lot of excitement about developments and innovation on the anode side. So I kind of jumped in the ring and have been leading Nanograph for quite a while now.
Nanograph's an interesting name for your company because, I know most of the anodes these days are graphite based. And so Nanographs kind of sounds like graphite, but you guys are actually replacing the graphite with silicon. Can you talk about that?
The origins of Nanograph, so we do use materials that are very small, hence the nano part of it. And the graph does not refer to graphite. It actually refers to graphene. And our company spun out of Northwestern University around 2012. At that time, there was quite a bit of excitement around graphene, right?
Yeah.
It won the Nobel Prize around that time. And people were wondering, hey, we have this really interesting material with so many new properties. Can it fix any old problems, right? And silicon anodes have a number of issues with them. There's two main ones. One is the SEI instability, and the other one is disconnection. So make a long story short, this company, or the students that started this company, started using graphene to solve one or two of the problems. Unfortunately, over time, graphene became an expensive solution to a difficult problem or complex problem. We actually, Nanograph and others in the industry found a cheaper way to do it. So technology has evolved over time. Let's just say that.
One other thing I think we should talk about a little bit too is that, I mentioned, the national security aspect of graphite, and we've been looking to replace graphite just because supply chain issues are potentially problematic, right? Could you speak to that a little bit?
Just to give you context, most of the battery production today occurs in Asia. And historically, it's been split mainly between Japan, China, and Korea. Over the last decade, or really I should say, over the last 2 decades, the Chinese government has put a tremendous amount of funding into the lithium-ion space to build a battery supply chain that was superior to Japan and Korea. And they've done that, right? It took them 20 some odd years. The government was pouring in subsidies year after year. They started taking back the subsidies in 2021. And they did that because there were just too many battery companies. And what happened in the battery industry in China is that they consolidated, and now we're left with some very, very strong players like CATL. Getting back to the national security issue, China owns or controls 70% of the world's global battery supply chain. So that's everything from materials to production, and even production of batteries, and also production of electronic equipment or cars and things like that. They dominate in that category. And so the national security concerns come from, well, if there was ever a conflict between China, the U.S. military would have a supply chain issue when it comes to batteries.
And graphite too, right? Because they own the minerals.
That too. Yeah. When we think about upstream things, China has made, for the issue of graphite, 85% of the world's natural resources of natural graphite occur in China. So they have all the graphite. And the graphite has been the negative electrode for lithium-ion batteries since 1992. China's also made many other investments, not just in graphite, but critical minerals, right? They've started mines, mining in different countries, Africa and other countries. to secure their supply of the elements that are critical to make a lithium-ion batteries. And those kinds of investments take decades to show dividends. Yeah. What I think China has been very good at is they've been doing this for 20, 25 years.
Yeah, and I know they had a big effort, big push to secure mineral rights throughout Africa too. So I think we were a little late to that game as well, right?
For sure.
So talk to me about the advantages of going with a silicon anode. I mean, besides the fact that silicon's everywhere and we have access to it.
So it's naturally abundant, and that's a good thing. So there's kind of three things that silicon really benefit lithium-ion batteries. So the first is silicon by nature, when you think about it on a weight basis, can store 10 times the amount of lithium that graphite can. So that's an incredible, an important property that silicon has. So what that basically means is you can add in silicon in small amounts and actually increase your runtime on an iPhone battery, for example. The other one that silicon also benefits is power density. So power density refers to how fast you can charge a cell and how fast you can discharge the cell. And this was actually the first area that silicon was used in. So silicon has a higher energy density. What it allows cell designers to do is make alterations, let's say, or changes in cell design that lower the resistance of the cell and allow users to charge faster or discharge faster. And that's used in a variety of different applications. The most common are things like power tools and vacuum cleaners and things like that.
Yeah, so things that have a heavy load.
Totally.
Yeah.
And the third one would be cost. As you said, as you had mentioned, it's naturally abundant. In theory, with the right scale, silicon anodes should be cheaper than graphite and can ultimately replace graphite. But as I said earlier, everything's incremental in the lithium-ion battery space. So you're beginning to see silicon be sprinkled in or added in at like 5 to 7%. And companies like Nanograph, where with this second or third generation of technology, we're trying to get that above 10%, right? Even as high as 20%.
I mean, that's a pretty big jump.
It's huge. Yeah.
Like you mentioned in describing, this how the cathode and the anode work, you're moving, some of that lithium up to the silicon end of the battery. And when you absorb that, there's a little bit of an expansion. And I know that's one of the big challenges with silicon, right?
Yeah, that's absolutely it. I think it's actually a little bit more than a little bit. It expands in theory about close to 400%.
That is not insignificant.
So that's not insignificant. So when you charge a battery that contains silicon, there's a variety of different forms of silicon. They all expand quite a bit. And when it expands, the particles fracture. And when they fracture, that creates a bunch of instability with the surface of the material. I think I mentioned the SEI before. And that has a cascading effect on its performance in a battery, right? Usually the most common thing we see is poor cycle life. But I would say over the last 5 years, there's a number of companies, Nanograph being one of them, that have come up with solutions to those pain points. So we're be able to generate cells that cycle 900 to 1,000 cycles, which is kind of puts it in EV territory. It's very exciting.
How does that cycle life differ from like a normal battery? What does a normal battery do, and like how many cycles can you get out of silicon?
You can get a lot out of silicon. Silicon can go, I would say, 1,000 to 2,000 cycles without an issue. There's a certain amount of degradation. In the industry, we usually say the cutoff, if you will, is about 80% of the capacity. So that is the case just historically. It's consumer perceivable. I think I learned in the Duracell days that if your capacity changes by 10%, consumers usually realize that, hey, my iPhone's not working the way it used to.
Yeah.
And by 20%, we call it a day. And it's time for a new battery.
One of the challenges you talk about is sort of the expansion of the silicon anode, which is 300 to 400% is quite a lot. So I know there's sort of like, it's sort of on that first charge, there's a bigger shift, right? Like how do you manage to that expansion and I would assume contraction too, right?
Yeah, let me try to explain this in a simple way. So we found a chemical method to what we call dope, or change the chemical composition of silicon, such that we like to call it pre-swell it. So it ultimately, this new combination or new chemical composition fundamentally has smaller swelling properties, but what we do is we pre-swell it. And what we found when we do that is that fracturing of the particles and all the things that happen that cascade down and create poor performance doesn't happen, or it's minimized, let's say.
Right.
And that, in a very simple way is what we're doing. We're trying to minimize those SEI, particle fractures, swelling, all of those things that are the pain points and the reason why people haven't been using silicon at 10-20%.
So basically, you've got this innovation, like how do you how does pre-doping the silicon anode impact the performance of the battery?
Like I said, it impacts the performance, and we've actually proved that. I'll show you an example here. So a little show and tell. So this is what we sell. This is silicon powder. See it in there. It's a blackish brown powder. It's silicon oxide. And we've hit a number of important milestones. We've been working over the last 3 years to get that powder into a battery. This is an 18650 battery. This at the time was literally the world's most energy dense cell. I think there's been other companies since then that have come up with something very similar. Nonetheless, the benefit here of what we're doing is more runtime, more so than we've seen in the past. The reason we achieve that is we can put much more silicon in there. And some of the early silicon cells had 5 to 7%, 5 to 7%, I should say. And this cell here is well over 20%. And we've continued to modify and optimize this cell in the lab, and we've actually been able to go even as high as like 30 to 40%. And that's all due to the changes that we've done in our silicon technology and product that makes it more stable and it allows cell producers to put just more of it in there and less graphite.
Well, and you mentioned 18650 batteries, and we see 18650 batteries, for those who are unfamiliar with them, that's a common EV battery too, right?
Maybe not so common anymore.
Okay.
So the first, when Tesla came out with their Model S and Roadster, this was the battery that they used. There were something like 8,000 of these, I think, in a Roadster or Model S. This was, you're right though, this is the oldest form factor. So lithium-ion was commercialized by Sony in 1992. I believe some of the first applications were camera and laptops. And if you remember, if you're old enough to remember, laptops were quite thick.
Yes.
And they would use, I think, 6 or 8 of these batteries in series and parallel to power your laptop back in the day when these things were, way big. It's less so of a form factor these days because through the 90s, everything was thin.
Yes.
Right? That was the name of the game. But we're headed back to this with EVs, right? So we're getting cylindrical cells that are bigger and bigger. Tesla's kind of driving that innovation there.
Obviously, silicon-based batteries have, more specific use cases, probably, right? I mean, so like where, and I know that like, when we talk national security issues, certainly, military and things like that come to mind around that. And I know you guys just had a really big announcement with Thales that maybe you can talk about. But maybe, let's talk about some of the use cases for these silicon batteries.
Yeah, if you just mentioned one, I'll start there. So one of the big milestones this year for our company is we're getting our product. So our product is this cell, which contains our silicon anode. We make this in the U.S. That's very important to the U.S. government. Mm-hmm. They've been very, very generous. They've given us millions of dollars to create the facility we have here. We have a second expansion facility to make the silicon here. it's so important for soldiers out there. The first application, so this news story about Talos was about handheld radios.
Right.
So these are the radios that even at the DNC, they're using exactly these radios out there, the security people. And our battery allows them to run longer. Now, that's not such a big issue at the United Center, but when you're in the middle of the desert and you're running out of juice, this is
And
really
people are
important.
shooting at you.
Totally. The other part of it that the military was very interested in, I didn't know this before we started working with them, but soldiers carry about 100 pounds of gear on their back.
Ugh.
25 pounds of that are batteries, believe it or not. So when they came to us, they said, we'll fund you if you can make a battery lighter and last longer. And it took us a little bit to actually, I'll call it 3 years of development time to get there. But we've done that, beginning to ship products out, to a customer, specifically the military.
I got to imagine that's pretty impactful. That's a lot of weight to carry around. And if 25% of it's battery.
it is. It's insane. I didn't know that. I wish I knew that earlier, because we as Nanograph as a company would have liked to have done something about that much earlier. But there's a whole slew of other applications where it's smaller footprints, lighter footprints. An example, okay, everyone has an Apple Watch.
Yeah. Sure,
that would be helpful. And, the dream of our company is to be able to get into vehicles, right? And what it means is we finally get rid of range anxiety, whether that's through faster charging or just the more energy dense cell.
Yes, please. I'll take a whole car full of those. Thank you.
Absolutely. I would love that too. I mean, it happens occasionally where I begin to worry about, where's the next charge station? But with these types of batteries in our technology, that should go away over time. And then the final thing with these is silicon should impact cost. And for electric vehicles, cost is everything, right? We see the EV market beginning to slow down, and those that are willing or able to buy more expensive EVs already did that.
Right.
And I think that the mainstream people are looking for example, Ford Focus that costs $25,000.
Right.
35% of the cost of an EV is based on the battery. So it's something we have to do a better job at in this country if we're going to have, as many million EVs on the road as President Biden wants there to be.
Like as somebody who owns an EV, I worry about like the batteries, because I know that it's a substantial cost. I mean, you're talking $20,000-$30,000 to replace these batteries, which is not insignificant, and which is one of the reasons why I think a lot of people are reluctant to. I mean, like for me, I lease my car because I don't want to have to be stuck with, dead battery pack and trying to sell a car off, right? So like a longer lasting battery, a battery that's less expensive so that maybe you could replace them and keep the car. I mean, those are all really, really positive impacts for the EV industry, I would imagine.
For sure. And that's part of the reason why silicon over the last 5 to 7 years has been a really hot topic. There have been billions of dollars poured into silicon anode companies, just with the dream or their understanding that this is a strategic technology that changes, our outlook on EVs and other things.
Obviously, you're talking about, adding silicon to the anode. I mean, you're in the battery industry. Where do you see the like most promising technologies, emerging in the battery space?
It's a good question. I'll kind of go out on the limb here. I'm old school and very conservative because I've been around a long time. I think I'll say there's a lot of things that are very sexy that are being proposed. Things like solid-state batteries, sodium ion, lithium metal. The excitement seems to go in circles. And for example, I worked on solid-state batteries for my PhD thesis. I know I'm dating myself, but that was like over 30 years ago.
Right.
And I asked myself, what's changed? The answer is not a whole lot. There's been a lot of investment dollars put into it, but the fundamental issues that they have, in my opinion, still remain. So I think a lot of these sexy things that people talk about will take decades to really come to fruition. To answer your question, there's more, let's call it incremental things that I'm seeing that are exciting that I think can have a big impact. One of them is dry electrode processing. So on the cathode side, we use, typically the industry uses a solvent, which is expensive. It's not great for the environment. There's a lot of cost in recycling that over time.
Mm-hmm.
What if you didn't have to use that? And it was just a dry electrode. And there's a number of companies out there that are doing well from what I hear. They're proving it out. There's rumors of it being, Tesla's had some success, and I think there's other companies, but it's small incremental improvements within a process that already exists that can reduce cost. I'm not an expert in that field, but every little bit counts in terms of decreasing the cost of batteries and then creating a car that, is 25,000 or 20,000 that people would want to buy.
In order to produce, silicon anode batteries, you've had to develop some, kind of novel technology to make that all happen, just in terms of process and making these and creating these things. And I've got to imagine some of the advancements you're making there will lend itself to other advancements down the road. Could you speak maybe to, where you feel like you guys are headed?
So I'll give it to you on two fronts. You started talking about the technology front. So a lot of the issues, we have a very good and competitive silicon anode today. But historically, the problems are on a fundamental level. There's an interaction, all these SEI and expansion things, they're very much coupled with the electrolyte. So our company thinks a lot about electrolytes. I think when you think about a holistic solution to silicon, it's not just going to be about a better silicon. It's going to be about a better silicon and a better electrolyte, or an electrolyte silicon combination that is optimum in terms of stability that can really take us to the next level. I think that's the next frontier for our company.
So are you saying like to add silicon to the electrolyte rather than just sort of an anode?
No, it's just electrolyte technology.
Oh, just electrolyte.
So companies, there's standard electrolytes that they use with silicon batteries, but there are additives, there are different solvents. All these little, and a lot of it is kind of magic in my opinion, but these combinations of, foo-foo dust that they add into electrolyte, we have seen, science has proven that actually impacts a lot of the pain points that we have now and probably will have for the next few years. So I think from a technology point of view, our company continues to talk to electrolyte companies as well as work on the silicon. I think it's a system approach. Maybe from a business standpoint, where our company is headed, the next thing is scale, cost and scale.
Right.
So we've reached, as I said earlier, we've reached our beachhead market. So it's the military. And honestly, we have an expensive material and expensive battery at the scale that we're making it here in Chicago. But we recognize that our technology is certainly good enough for electric vehicles. But for it to be attractive to EV OEMs and the people that make the batteries for the car companies, we have to scale
massively
to a place where, the dollar per kilowatt hour is very similar to graphite, if not better.
Yeah.
And that's a pretty big undertaking. So that's the next stage of our company. So we've reached that hockey stick inflection point. And where you go from here is scale and cost.
Right. Well, and I know you guys you're building a facility in Chicago now that's going to be manufacturing some of this, correct?
Some of it, but it's still on a small, what I'll call a small scale with respect to what you're seeing in China.
Right.
For us, and I'll say we are applying or in the process of applying for some of the, government funding that's out there, like the bipartisan infrastructure law. These are all things designed to help catalyze companies that are ready, that have a technology and a business plan that's stable, or in a company that's sustainable to go to the next level. So our hope is to be able to leverage some of these things and take it to that next level, like 2 orders of magnitude more.
Yeah, that's amazing because I'm all for the cheaper, denser batteries. All I can say is keep up the good work, keep up the pace of innovation because you're making the batteries the world needs. And I just want to say thank you so much for coming on and telling us about Nanograph. Really appreciate it.
Yeah, I appreciate it, Chris. Thank you for the time and the opportunity.
Thanks so much. Thanks for watching. I'd love to hear from you and your opinions about battery tech in the comments. And if you could, give us a like, think about subscribing, and I will see you in the next one.